This is a video to help with the concept of permutations and combinations that we see in math notes in Chapter 10. You need to read this whole section because it gives some formulas and it brings in some new words, permutations and combinations. And the first thing we notice is that with permutations, it's going to talk about a list in which order matters, meaning there's a first place, a second place, a third place. It matters what order the things show up on a list. Combinations, order does not matter. Instead of it being lined up and there being a first, second, third, or fourth place, it's just a group of things. It's just almost like marbles in a bowl, that there's no order to where they are. So, first of all, I want us to, again, talk about the fact that permutations are when order matters. The numbers 1, 2, 3, 4 in a list are different than the numbers 4, 2, 1, and 3. Because permutation, the order in which we list those things, is different. Versus a combination where order does not matter, and therefore 1, 2, 3, 4 and 4, 2, 1, 3, even though those are in different orders, it's the same combination. It's just the digits 4, 3, 2, 1 in any order you want to say. And so here's two examples. The first example is there's people, A, B, C, and D, and they run in a race, and at the finish line, there's definitely an order. There's somebody came in first, and that was person B. And somebody came in second, and that was D. It would be very different if D was here and B was here. It makes a difference in the order. So this is a permutation because order matters. Now instead, take those same people A, B, C, and D, and if we're going to pick people to be on a committee, it doesn't make any difference if I pick person A first or I pick person B first. It really won't make any difference. They're both going to be on the committee. So order does not matter, and therefore this would be considered a combination. Now, in the next two problems, 10-20 and 10-21, we're going to be using either combination or permutation. We have to determine, does order matter? And in problem number 20, order is not important. It's just about picking some people. It's just who's going to be chosen. And since order does not matter, this is going to be a combination. And so it's going to be 12 people, choose any 3. And it won't matter what order you pick them, just so long as you pick 3 people. You choose 3 people. There's a notation for that, and this is the notation where you have a 12, choose 3. That's how we say it. This 12 is down low, kind of like when we do subnumbers, and this is 12, choose 3. In the previous math notes, there was a formula for this, and so you have to go back and look at your math notes to find the formula, and that is that a combination is written as the permutation, 12 permute 3, which is an ordering, and we divide by 3 factorial. And we're going to be using a lot with factorials with these combinations and permutations. So the next thing, well, that didn't help me because this is just one formula that gave me in its formula another formula. Well, this part here, 12 permute 3, is done by 12 factorial divided by 12 minus 3 factorial. This part right here is 12 permute 3. And then we're also putting 3 factorial in the denominator. And this right here is how we will compute 12 choose 3. So what does factorial mean? Factorial means you're going to multiply all the numbers descending from 12 all the way down to 1. So you've got 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And all of that is 12 factorial. Now in the denominator we're going to have 12 minus 3. Well, that's 9 factorial. So down here we're going to have, down in the denominator, we're going to have 9, 8, 7, 6, 5, 4, 3, 2, 1. And there it is, and that's 9 factorial. And then we can't forget that there's also another 3 factorial, which would be 3, 2, 1, all multiplied together. Since everything in the numerator is being multiplied and everything in the denominator is being multiplied, we can start canceling common factors. And we've got that 9, 8, 7, 6, 5, 4, 3, 2, 1, both numerator and denominator. And now we have 3 times 2 times 1. Well, 3 times 2 is 6, and so we can cancel that with the 12, and we're left with a 2. And that leaves us with 2 times 11 times 10, which means there are 220 ways to choose 3 people from a list of 12. That's how many different ways you can choose 3 people without any order. The next problem, this one is 5-digit combinations for a lock. Now this is kind of a funny thing because it's called a combination lock. It says that right here. Combination lock, which is actually the wrong words when you think about it mathematically. Because if you have a locker or any kind of a lock, the order in which you put the numbers matters. So even though we call them combination locks, they're actually permutation locks because order matters. So it's a permutation that we're looking at here. So in this problem, for her lock, there's going to be 5 different numbers that she's going to put in there. And in the first position right here, you can have any of the 10 digits 0 through 9. So there's 10 choices, 10 possible digits, and you're going to pick one of these. And then in this next slot, we can't have a repeat. So whatever you picked for this slot, you've now got 1 less, so you've only got 9 possible digits. We don't know which digit was picked, just know that there's only 9 left to pick from. And the next slot, now there's only 8 digits we can use. And the next slot, there's only going to be 7 digits. And the last spot, there's only 6 possible. And to figure out how many total different is just to multiply those numbers together. 10 times 9 times 8 times 7 times 6. And when we do that, there's 30,240 possible lock permutations. Different orderings of numbers. Okay. Now remember, since order matters, if I had the locker combination 1, 2, 3, 4, 5, that would be very different than a locker combination that was 5, 4, 3, 2, 1. In the second possibility, it's still permutation because it's this combination lock, so permutation lock actually. But this time we can repeat digits. So since you can repeat digits, now the first number that you would use with your combination lock or your permutation lock, there's 10 possible digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Since we can allow for repeats, we still, in the next spot, have 10 possible choices. And that continues on with all 5 of them, that there's 10 possible every single time. And so you could, theoretically, have a combination that was 0, 0, 0, 0, and 0. In fact, a lot of times when you buy locks to begin with, sometimes they have something as simple as that as their opening lock. So we're going to do 10 times 10 times 10 times 10 times 10, which is 10 to the 5th, which is 100,000. Next problem. It's about this bowling problem, and you have 2 different things going on here. The first one in 10-36, they're going to just pick 4 players. You've got a group of 6 people, and we just want to pick 4 players to play the game. Since you're just picking 4 people, it doesn't matter who you pick first. Order is not going to matter, so it's just a combination. 6 players choose 4. And as we saw before, we use that notation, 6C4. We say 6 choose 4. And we use permutations to calculate combinations. And so we've got 6 factorial for when it says 6P4, we're going to have 6 factorial. Then we're going to take the 6 minus the 4, right here, 6 minus 4. And we've got that for the 6 minus 4 factorial in the denominator. And then don't forget, we have another 4 factorial that we put down here. And 6 factorial is 6, 5, 4, 3, 2, 1, all multiplied. 6 minus 4 happens to be 2, so you've got 2 factorial, 2 times 1. And then we have 4 factorial, which is 4, 3, 2, 1, all multiplied. Do our canceling of things that are common, and that 2 goes into 6 3 times. We've got 3 times 5, which is 15. And so there are 15 different ways to choose 4 players when you've got 6 people to choose from. In the second part, it's the actual lineup. Now, in this case, it's an arrangement. It's, it matters who's going to play in the game first. So even though you've picked your 4 players, the order in which they play will matter. So this time we're going to have 6 players, and we're going to arrange or permute 4 of them. So it's 6p4, which is 6 factorial divided by 6 minus 4 factorial. Remember that this is just 2 factorial. So we've got 6, 5, 4, 3, 2, 1 divided by 2, 1. Cancel out those things that are common. You've got 6, 5, 4, 3, which is 360 different ways to arrange the players.